There I am. Thanks, Casey. I forgot to unmute my mic. So, hello everyone. Okay. So, Math 1410, and we are um on the eve of our first test, if you will. Um, all right, good to see you. Let's see. Amy, Dunia, Marcel, Zamana, Whitney, Fatima, Gregory, Fania, Azetta. I think, is that everybody? I think there may still be more people coming in. I'm here. I keep hearing dings. Okay. All right. So, one more reminder about our upcoming test, which is scheduled for next Monday, but the test will be posted on Sunday, 12:01 a.m. Central Time, and uh, and it is due on Monday, 11:59 p.m. Central Time. Hi, Amy. Do you have a question? Feel free to chime in or put it in the text in the chat box. I see a hand next to Amy's name. Um, so if anyone needs to ask a question and you want to chime in, just unmute and start talking. All right, that's how we do it here. My last class is really good at doing that. My last class from my last quarter, I'll be like saying whatever, and suddenly someone just chime in, say, question, I got a question. Seriously, which is totally fine. I'm actually kind of used to that, so I'm not used to you guys being so quiet. Anyways, all right. So if you have questions, feel free to chime in. Otherwise, I'm gonna keep talking. So test is gonna be posted Sunday night, I mean Sunday morning, and it's due on Monday night. You have up to 48 hours to work on that thing. It is not it should not be super long or super difficult. I'm using material that, that makes up your homework and things like that. So, um, as long as you've been doing your homework, okay, I think you're not going to see any surprises. Okay. Um, I kind of want to um, give you guys a heads up that I see that, while many of you are on top of your homework, but I see a few people who are behind. All right. I know that I'm very generous in terms of the due dates and the fact that I am not um, enforcing hard deadlines for this class. But I am concerned that, if you are behind on your homework because, at the end, everything kind of catches up and anything you haven't done, it's going to become zeros, and that could be a problem. And the other is that, when we have a test, well, how you're going to study your tests if you haven't done your homework, right? I mean, so um, look at your homework as your preparation for the test. Okay. Um, please do them. Okay. There are no freebies in this class. Um, I can't give you free pass on your homework just because you pass your tests. Okay, you cannot test out of this class. Okay, so even if you do well on tests, I still need to see your homework completed. All right. Any questions or comments about that? So make sure you do homework. We're going to cover up to section 2.5 today. So you're gonna have 1, 1, 1, 2, 1, 3, I think, and then 2, 1, 2, 2, 2, 3, 2, 4, 2, 5. So that's eight homework assignments plus quizzes. All right. So if you're behind, let's try to get it done. Okay. All right. Any questions or comments about anything? Okay. Um, so one more remark about the test. As I mentioned, the test is going to be posted on Canvas. There's going to be detailed information on how to download and how to turn it in and when it's due and all that stuff. It's going to be posted in announcements. Okay, so after class between now and Sunday, I'm going to be posting on announcements, how to access the test and take it and submit it. So make sure that you read that carefully, follow the directions. Um, the test itself, it's not timed. There's no time limit. Um, However, it depends on, and I still haven't made up the test yet. Talk about putting everything to the last minute. Um, I may put something in that that is covered, with from what we've been doing. Um, but it is something that I'm gonna see, how you guys are able to follow directions. Okay. Um, I mentioned that, the problems are similar to what you see on the homework, but there may be um, some other activities on the test that may require you to, like for example, I may ask you to hand draw a graph and make a frequency table and things like that, and so if you are given data to do that, so make sure that you do it correctly and so forth. Okay, so just follow the directions. All right. Okay. Um, any questions or comments before we start? All right. The lecture and the homework demo will be posted shortly after class tonight. The one on Wednesday took a little while because YouTube was not not friendly on Monday, so I didn't get it on. I think not till was it yesterday or was it this morning? But hopefully tonight's lecture will be up shortly after the end of the class. All right, so without further ado, let's continue. So today we are continuing on measure of variations. So we're talking about spread, okay? And then we're going to go into a section talking about the measures of position. So let's get right into it. So last time, if you remember, when we are talking about measure of variation, measurement of spread, okay, I was saying how, you can have two distributions, okay, with the same center, okay. One may have a larger spread than the other, okay. So everything that we talk about spread kind of revolves around that idea. So here is a picture, or here are pictures of um, the measures of standard deviation. Now, if you're not sure what standard deviation is, all you have to think about is that it is a measure of spread. All right. Kind of like range. Okay. But a little bit more sophisticated. So think of um, think of standard deviation as something that's similar to range. Okay. Now, we are looking at three pictures here. Okay. Um, and they all have the same center. Okay. They all have a mean of 5. All right. They all have the same center. Mean is at 5. Okay. But you can see that the shapes are very different. Okay. The first one, you know, has no standard deviation. Standard deviation equals to 0. So it has 0 spread, okay, because everything is exactly piled up in the middle. The second one, okay, it's a little bit more spread out, okay, but it's still very much, centrally located. And you see that it has a standard deviation of 1.2. And the last one really spreads out, okay, because, this is what it looks like, okay? And remember, since the spread is a measurement from the center and you have a lot of data points far, far away, on either end, and that's why this distribution has the largest standard deviation at 3.0. Okay, so as you can compare, the standard deviation is a measurement of spread, and you can see the difference between the first one, the second one, and the third one. Okay, first one is 0, second one is 1.2, and the last one is 3.0. All right, so very, very different. Okay, let's see some more pictures. Okay, here is um, without calculating, estimate the population standard deviation of each data set. Okay, so what are we looking at here? Okay, so the first one, I want to say that the standard deviation, the population standard deviation, is 0. Okay, because everything it's in the center. Second one, I'm not quite remembering how these supposed to go. So let's find out how they get the standard deviation of each data set. All right. So let's look at the next one. Okay. So the first one, as I guessed, is correct. Okay. It has a standard deviation equal to 0 because everything is in the center. The next one. Okay. So the next one. So so there are 8 entries in this population. Okay. Each of the each of the 8 entries has a standard deviation of plus or minus 1. So 4 is in the center. So they're either at 3 or at 5. So if it's at 5, they are plus 1. If it's at 3, it's minus 1. Okay. So um so if we do that calculation, okay, we're going to see that it has a population standard deviation equals to 1. All right. The next one. So the next one, we have deviations of either plus or minus 1 or plus or minus 3. So this is a plus 1, this is a plus 3, that's a minus 1, that's a minus 3, right? Um, so the population standard deviation would be about 2, okay? By calculating, okay, if we actually get the data, plug them into the formula that, we were learning last time, we would get a population standard deviation of about 2.2. All right, so the last one is 1. Okay, as you can see that the two bars are closer to the center. Okay, whereas 2.2, you see that they are more spread out. All right, so let's talk about how does this measurement of spread works. Okay, so we've been saying standard deviation many, many times, but just exactly how does it work? All right, so I'm gonna show you how it works. So if we have a bell-shaped distribution, all right, and this is the center is in the middle, all right. Um, Now, let me put an example into this to make it a little bit more real for you, okay? So let's say that, um, we're in a real class and I gave you guys a quiz, all right? And let's say the quiz is 100%, it's 100 points, and the score that from your scores are bell-shaped distributed. All right. And so I calculated, the mean. Okay, the mean is 70. All right. So that's the average. All right. And I calculated the standard deviation of all your scores. Okay. And your standard deviation is 5. Okay. So let's see how this works. Okay. So your scores are in a bell-shaped distribution. Okay. And 70 would be the center, the mean. Okay. Now, if you score a 75, remember, standard deviation equals to 5 means that if you go 5 points over the mean, you are at +1 standard deviation. Okay. Now, if you score 80 points, okay, now you are +2 standard deviations. So standard deviation is a measuring unit. Okay. Now, on the other side, if you score a 65, if you score 65, you are at -1 standard deviation from the mean. And if you score 60, you are at -2 standard deviations from the mean. Okay, so once again, standard deviation is actually a measuring unit. All right. Okay, so now that you know how this standard deviation can be converted to a measuring unit in a distribution. So what else? Okay, how else is what does this all mean? I'm gonna tell you. All right. In any bell-shaped distribution, okay, the amount of data between +1 and -1 standard deviation, okay, such as this part in the picture, okay, this piece here, okay, this is 68% of the data, which means that, in the class, 68% of you scored between 65 and 75 points. Okay. So let's look at this bell-shaped distribution differently. Okay. So imagine that, this bell-shaped distribution is a cake, all right, cake that you can eat, okay, birthday cake or whatever. People in my class like to call it a chocolate cake because I think people like chocolate. All right, so think of this bell shape as a chocolate cake. Okay, chocolate cake. Okay, we'll cut it into bell shape. All right, now if I cut the cake at between -1 standard deviation and +1 standard deviation, okay, so I'm gonna cut the cake at those two spots. So how much cake is there between those two cuts? 68% of the cake. That's a big piece of the cake, right? Okay, so 68% of the score falls between plus and -1 standard deviation. Okay, now if we looked at how much cake there is between 60 and 80, so now we're going into plus and -2 standard deviations. All right, so I'm going to add the two side pieces, okay, to the centerpiece. So if I cut the cake at +or -2 standard deviation, okay, now I have 95% of the cake. All right. You understand what I'm saying? 95% of the data falls between +or -2 standard deviations. Okay. So between those two cuts, 95% of that chocolate cake. Okay. And if I go further, okay, and if I go to, let me redraw the cake. All right. If I go to +or -3 standard deviation, okay, so 3 standard deviations would be, okay, so mean is 70, standard deviation equals to 5, so 3 standard deviations would be 85, right? So this would be +3 standard deviations, okay, and then -3 standard deviations would be 55, okay, so -3 standard deviations. Okay, so now this piece of cake in between, 99.7% of the cake. That's pretty much the whole cake. All right. So that means that, between 55 and 85, that's practically, what everyone got on the quiz. Okay. So, um, so think of standard deviations as a measuring unit away from the center, and using the standard deviation, okay, it will tell you the amount of data you have, okay, in between or around those cuts. All right. So let's see if they show something like that. I think they do. There you go. So that's their version of the chocolate cake. Okay. So as you can see, okay, although I like my version better, okay, so this is how they mark +1 standard deviation. This is minus one standard deviation. So this is 68%, okay, because it's 34% to the left, 34% to the right. Okay, and then here we have ±2 standard deviations. Okay, this would be 34 plus 13.5 each side, which would give you 47.5. Yep, 47.5. So together, 95% within two standard deviations. Okay, 68% within one standard deviation. And then we go three standard deviations. Okay, now we're at 99.7% of the entire cake. All right. Okay. Um, any questions on this? This applies to any bell-shaped distribution. Okay, so you can say that, well, does this work for everything? Yes, it does. Okay, think of the standard deviation unit as kind of like, there are 12 inches in 1 foot. Okay, in any bell-shaped distribution, if you go ±1 standard deviation, always 68%. Okay, if you go ±2 standard deviations, always 95%. Okay, so these are measuring units. All right. Let's look at some examples. I think we're going to see some examples coming up. All right. That kind of helps you see this. All right. Here we go. So, in a survey conducted by National Center of Health for Health Statistics, the sample mean height of women in the United States was 64.1 inches. All right, with a sample standard deviation of 2.6 inches. In case you wonder, you see that, we're using population standard deviation and sample standard deviation interchangeably. Okay, don't worry, it works both ways. It works for the population and it works for the sample. Okay, as long as we are talking about standard deviation, the spread works the same way. All right, so this one is a sample with the mean at 64.1 and a sample standard deviation at 2.6 inches. So estimate that percent of women whose heights are between 58.9 and 64.1. Okay, so let's draw that picture of our chocolate cake, our bell-shaped curve. Okay. Now, the mean is 64.1. Okay, so that's the center. All right. Before I be, be- before we go before we move forward with this, now let's just say that if I'm going to cut the cake right dead center at 64.1, okay, what's the what's the uh, um what's the percentage of the people taller than 64.1? Look at this, okay? We pretty much cut it right in the middle, okay, which is what the mean is. So the uh, percentage of women who are above 64.1 inches would be exactly 50%. Okay. Same with women who are below 64.1 inches, which is 50%. Okay. So what I'm trying to tell you is that, you know, uh, if we cut right down the mean, right down the center, okay, it is 50-50 from that point. All right. Back to our example. Now, our measurements, okay, the mean is 64.1. The standard deviation of that sample is 2.6. All right. And we want to find the amount of percent of women between 58.9 and 64.1. Okay, so let's see. So 58.9 will be to the left of that. Okay, 64.1, once again, that's in the center. All right, so let's take a look and see exactly how many standard deviation it is. 64.1 minus 58.9. Okay, so that's 2. So 5.2, right? Okay, now 5.2. Okay, now remember, standard deviation, each unit is 2.6. So 5.2, this equals to 2 standard deviations, right? And in this case, it will be 2 standard deviations to the left. Okay, so this measurement here, this is 2 standard deviations. Okay, now if you go back to that previous picture showing you the percentage, okay, if you can see, so 2 standard deviations on to the left to the center. Okay, so this would be 34% plus 13.5%, right? Okay, so this would be, um, so you add these two together and you get 47.5%, which would be the percentage of women between those two heights, 58.9, 64.1. So this is going to be 47.5% of the women. So let's see if they got the same thing. All right, so yes, so they show the same picture again. All right, so 34% plus 13.59%, and that should give us 47.5 or 47 point something. So 47.72. Well, I was saying 47.5%. Close enough. All right. One thing you're going to find out when we do statistical calculations is that we don't always get the exact same number, especially when there are decimals after these numbers, um, depending on, which source you're looking at. So, but I would say 47.5 is just fine because, if you remember, okay, plus or minus 2 standard deviation is 95%. All right, 95% plus or minus 2 standard deviation. So since we're only taking half of that, okay, so 95 divided by 2 would be 47.5%. All right, let's look at another page, another example. Okay, so any questions on that last example? Basically, it was trying to show you how the measure of standard deviation works, in within the data distribution. Okay, so the measurement, converts to the portion of data that you have. All right. Okay, so next we're going into Chebyshev's theorem. Yep, Chebyshev's. Um, Chebyshev's theorem, it came from a long time ago. Um, and it is a rough estimate of standard deviation. It's a rough standard deviation estimate. All right. Um, so one thing that you should be aware is that this is not necessarily the actual standard deviation, but it's a very rough estimate. Okay, so if you use this formula to calculate standard deviation, well, to estimate the standard deviation, and you say, well, but why is this off by so much? Well, that's because it's a very rough estimate. Okay, so I'm going to show you what you're seeing here. Okay, so the formula, okay, it goes like this. The portion of any data set lying within k standard deviations of the mean is at least, okay, 1 minus 1 over k squared. All right. So if k equals, and this only works when k greater than 1. Okay. So we cannot even use it to estimate when k equals to 1. All right. Which means that we don't get to, because so one standard deviation, if you recall, is 68%. Two standard deviations, okay, it's 95%. And three standard deviations is 99.7%, right? Okay, this is from the actual calculation, okay, of the picture that we showed you previously. Now we're looking at a rough estimate, okay, from a long time ago, before they know how to do these calculations. So if we have k equals to 2, okay, the rough estimate would be 1 minus 2 squared, or 3/4. Okay, so I put the 2 into this formula for k. So 1 minus 1 over k squared becomes 1 minus 1 over 2 squared, which is 3/4, which is 75%. Okay. But isn't that supposed to be 95%? Yes, it is supposed to be 95%. So this is, when I say rough, it's a really rough estimate. Okay. But remember, the keyword here is that at least. So it is at least 75% of the data. Okay. So the theorem is valid, although it is off by quite a bit. Okay. Now let's look at k equals to 3. K equals to 3. Okay, we plug in 3 into that formula, and we get 1 minus 1 over 3 squared. Okay, so which is 8 over 9, which is 88.9%. Okay, and what's the actual standard deviation percentage? It's 99.7%. Okay, um, so in a way, it is true because it is at least 88.9%, but not by any means close. All right. Um, Although the thing about this particular formula, okay, the word that you should look at is any data set. So when we were doing the 68%, 95%, okay, we are talking about a bell-shaped curve, okay? But when we say any data set, okay, it can be a data set that has a uniform distribution. Okay, if we have a uniform distribution, okay, then maybe the um, maybe the estimates would actually be closer, or be closer to those particular standard deviations for those distributions. All right. So, all right. Um, so here is an example using Chebyshev's theorem. Okay, and as we can see, we have two distributions that are not bell-shaped curves. Okay, which means that Chebyshev's would actually, be a good estimate to figure it out what it is. Okay, so the example here is we have the age distribution for Georgia and Iowa. Okay, and we want to find, okay, the um, percentage of data, okay, within plus or minus 2 standard deviations. Okay, k equals to 2. All right. So when we do k equals to 2, if you remember, 1 minus 1 over k squared would be 1 minus 1 over 2 squared, which is 1 minus 1/4, which is 3/4 or 75%. All right. So is an age of 90 unusual? All right. So 90 would be here. Okay. If you look at, it would be like at the very, very end. Okay. Um, okay. So let's see how they show this. Okay. So, so when we are looking at plus or minus 2 standard deviations from the mean for those two distributions, okay, for Georgia, okay, we're looking between from 7 to 83.4. From 7, which would be about here, to 83.4, which would be about there. All right. You can say at least 75% of the population is between those two. Oh, -7. I didn't even see, I didn't say negative. So not only it is 7, it is -7. So -7 in this particular data set, we're just stack counting from 0. Okay, so this amount of data, okay, it is at least 75%, probably a lot more. All right. And if you have an age of 90, okay, it lies more than 2 standard deviations from the mean. So this age is unusual. Okay, so if you ever have a question about whether a measurement is unusual, okay, the rule of thumb is 2 standard deviations. Okay, so 2 standard deviations will is the judgment call. All right, so if it's more than that, then yes, it is unusual. All right. Um, so if we look at the next one, okay, 39.8, 23.7. Okay, so 23.7, we add and subtract that from 39.8. Okay, if as a matter of fact, if we do 2 standard deviations, okay, so 23.7, this would be 47.4. All right. So if we so the left end, okay, 39.8 minus 47.4, that's going to be a negative number. Okay, so our starting point is going to be at 0 again. Okay, and the right end is going to be 39.8 plus 47.4. Okay, so that's going to be 87.2. So that's going to be like pretty much the end here. So once again, 2 standard deviations is from 0 to 87.2. Okay, so Cheryshev theorem holds, okay, at least 75%. Okay, now if you have an age of 90 for this second distribution, but guess what? 90 is still beyond 2 standard deviations. Okay, because 2 standard deviations ends at 87.2. So if you have an age equal to 90 for Iowa, it is also unusual. All right, because it's beyond 2 standard deviations. All right. Any questions on that? All right. If you have questions, feel free to put it in the comment box, or if you want to raise your hand, I'll try to see if I can see your little hand signal. All right. Okay, so now next thing we're going to do is we're going to look at group data. Remember last time we were looking at group data. So group data basically is that you have a frequency table and it gives you the frequency for each category. Okay. But you may not have the actual data that were sorted into the frequency table. Remember that? So how are we going to use the information from a frequency table to calculate the standard deviation? Okay, well, um, the short answer is that, same strategy. We're going to use the midpoint and pretend um, every data point is that midpoint value. All right, if you remember that. So, um, so as it says here, when a frequency distribution has classes, estimate the sample mean and standard deviation by using the midpoint of each class. All right, since we may not have the actual data, our best estimate, our best guess is, using the midpoint. Now, here is a 50 numbers of children in households. Okay, so this is the actual data. All right. Now let's find the sample mean and standard deviation of each data of the data set. All right. So you may use any technology at your disposal to do that. All right. But I think they did it for us. So um, the mean, okay, the mean of the 50 numbers is 1.8. All right. Um, so what we have here is we sort the data into categories. Okay, so let me show you what the data looks like again. So this is the data. Okay, so we're going to sort 0, 1, 2, 3, 4, 5, 6. Okay, because I don't think there's anyone with more than 6. So we're going to sort that into each group. All right, so for example, we have 10 households with no kids. Okay, 19 has 1, 14 has 2, and so on. Okay, so we add up the total number of kids, okay, divide by total number of families, and we get 1.8. Okay, so how are we going to calculate the standard deviation for this group? Okay, so remember the formula or the process to calculate standard deviation is step one. Okay, we're going to take each data point, subtract from that the mean. Okay, and then step two, we're going to square the differences. Okay, and then number three, okay, we're going to multiply the squared difference with how many data points it has. Okay, so for example, if we're looking at the first group, okay, the one where the families have no kids. All right, so the data point would be 0, okay, minus 1.82, which is the mean. So it's negative 1.82. Okay, for the first step, we square that. We get 3.3124, which is step 2. And since there are 10 data points of that value, we multiply that squared difference by 10, and we get 33.124. Okay, and we do that for all the other um, categories. Okay, and we get a sum of 145.38. All right. Now we're not quite done yet because there's going to be one last step. Okay, so 145.38 is what we call sum of squares. And then the next step would be to divide by n minus 1. If you recall, for the sample standard deviation, okay, this is our sum of square from last page. And we'll divide that by n minus 1. Okay, since there are 50 families, n minus 1 would be 49. And we get sample standard deviation of 1.7. All right. All right. So let's take a look at a different distribution, a different frequency table. Okay, now this one um, has data values that are sorted into different categories. Okay, so this figure shows the price ranges in thousands of dollars and corresponding number of homes, okay, listed in a mid-sized US city. Okay, so the way to read this is that, there are 129 homes between 100,000 to $199,000. Okay, and there are 39 homes that are between 200 and 299, 22 homes between 300 and 399, and so forth. Okay, there are 173 homes that are less than $100,000. Okay, so that's the data. Now, do we know the actual sale price of every home? Well, if they don't provide the data and they just give us this pie chart, we don't have it. Okay, so in order for us to try to find the mean and the sample standard deviation, we're gonna have to, yeah, use our best guess and use the midpoint of each category. All right. Um, so And one of the problems that we have, okay, for this kind of grouping is that now each of these, okay, we can get the midpoint. Okay, this would be like 445. So 899 would be 459. Wait. Okay, so for a group such as 400 and 499, so 449, and we add them up, 899 divided by 2. Okay, this would be 449.5. Okay, so the midpoint would be 449.5. And we would pretend that all 8 homes in that price range, they all have the value of 449.5. The problem with this particular example is that we have a group such as like this one, 500 or more. Okay, and also, well, less than 100 is not as big of a problem because this is basically 0 to 100. Okay, and we can use 49.5 for that. But for 500 or more, well, how do we get the midpoint of that? Well, we would just have to assume that it's 500 to 599 and use 549.5 as our estimate. Okay, which would not be accurate if you have some, you know, homes that are millions of dollars or things like that. Okay, but our best guess would be, just assume that, the highest level also have the same width. All right. Okay, so let's see how this goes. Okay, so this is what they're talking about. Okay, when you have your last category as open-ended, that kind of becomes a problem. Okay, so here is our data table, our frequency table, uh, with the midpoint, included. Okay, so for 0 to 99, we're going to use 49.5 as the value for every home. Okay, so same thing with all the other categories. Okay, we're going to use the midpoint. Okay, and apply that to every data value within that category. Okay, um, so we take the midpoint, we multiply to the frequency. So this would be the total of that category. Okay, so total for the first group, total for the second group, and so forth. Okay, so now the mean, okay, which is the first thing we need when we calculate standard deviation, we need to find the mean first. So we get a total divided by number of data points. Okay, so 154.5 is the sample mean. All right, so let's follow along. The next step would be, okay, so first step is find the mean. Okay, then the next step would be to find the differences of each data point and the mean. All right. And then after that, we're going to do the square of the differences. And lastly, okay, we're going to multiply the square times the frequency, okay, to get the sum of squares. So sum of squares would be this number, okay, and then we're going to divide this by n minus 1. All right. So um, so this would give us 139.4 would be our sample standard deviation. Okay. And that would be our answer to the question. All right. Sample mean is 154,500, and then the sample standard deviation is 139,400. Okay, for that data set. So if you want to see how, we're going to do that in our homework problems, okay, I'm going to be doing some examples in the homework, and, and so you can see how we're going to do it. All right. All right. Any questions on this particular example?
I
Okay.
did actually. Can you, for the last one, I didn't understand where n came from. The other numbers make sense, but where is 389 or I guess 340? Where is that
Okay.
coming from?
Okay. So, um, remember n is the sample size. Okay. So, the in the data we have, okay, so I didn't say here. All right. So here is our frequency table, right? This is the frequency table with all the homes and their prices. Okay. So the frequency, so how many homes are there in each category of prices? And the total number of homes in our data is 390. Okay. So this is also our n, okay, which is sample size. So in our survey, in this particular survey, we surveyed um, 390 homes, okay, and therefore, good, uh, the calculation for standard deviation, which we use n minus 1, would be 390 minus 1, which is 389. All right. Okay. Any other questions? All right. Okay. Uh, Here's another example. Oh wait, no. Nope, that was it. All right. Um, so if you're not completely understanding it, I would like kind of watch it again, just so that you understand where all the numbers come from. Because in an example like this, we have a ton of numbers coming through. So if you're not keeping a close eye on where everything is coming from, the next thing you know is like, well, I don't know what all the numbers are, and why we're doing all that kind of stuff. So it would be good if you are able to slow down and slowly follow every piece of number that comes in and out, okay, of the calculation. All right. Okay. So now we're going into measures of position. Okay. If you wonder what that is, well, we actually kind of started talking about it. All right. Um, with the median. Okay. So actually, so if you have 1, 2, 3, 4, 5, 6, 7, let's see. Uh, all right, so say I have 11 data points. All right. The median would be the middle value, right? We're all okay with that. Okay. Now we're going to add more to it. Okay. So if we look at the first half, okay, and the second half, all right, within the first half, 3 is the middle. Okay. So what's that called? That's called um, quartile one or first quartile. Okay. So think of first quartile as median, the median of the first half. All right. And the third quartile, which would be nine, this is called a third quartile. Okay. Or median of the second half. All right. And if you wonder where the second quartile is, well, second quartile is the median. All right. So this is what we mean by measures of position. All right. All right. So let's see how they present it. Okay. So we are looking at first, second, and third quartile. All right. That's the median. How to find interquartile range. Okay. Interquartile range would be the distance between Q1 and Q3. All right. And how to present a data set graphically using a box and whisker plot. Okay, those are fun to draw. How to interpret other fractiles such as percentiles, or for percentiles is always it's also a good measurement. Okay, it's kind of like, okay, well, if you score 95 on a test, okay, how much better are you than everyone else? Okay, if you find yourself to be in the 90th percentile, that means you're better than 90% of the people. All right, that's what percentile means. All right, and then finally, we're going to unveil the z-score. All right. Okay, so let's go into it. Okay, so first thing, quartiles. Okay, so exactly how I described it. All right, so quartile is about 1/4 of the data. Okay, um, so if I separate my data into four parts. Okay, the middle is median. Quartile one would be here. Quartile three is here. Okay, so first quartile would be, you know, quarter of the data. Okay, so each quartile is 1/4 of your data points. Um, all right. Fractiles are numbers that partition and order data into equal parts. So when we dice up our data. Okay, that's what we're doing. We are creating fractiles. All right. Okay. Now finding quartiles. All right. So I kind of show you guys how to do it. Okay. Now if you have a very even number of data points, 11 or something like that, or 15. Okay. If you have 15, okay, so you can do the middle one, and you still have seven to the right. Okay, and seven to the left. Okay, and with seven, okay, then the fourth one would be the median of the first half and median of second half. All right. Um, a good thing to remind you guys is that if you use StatCrunch on a problem with a data set, especially if it's a large one, it will find the first and third quartile for you as well, in addition to the median. Okay, so that comes in very handy. Because a lot of times your data is not exactly, you know, your data points is not exactly an amount that can be nicely divided into four parts. Okay. Um, so here's an example. We have 25, okay, data points, and find the first, second, and third quartile. All right. So um, when you have a large amount of data, you have to sort it, and then you have to count them and all that kind of stuff. So even 25 data points, it's going to take you a couple minutes to figure out, what the first and third quartiles are and the median. Um, so let's see how they do it. All right. So they use technology. Okay. So And we can do that too. Okay, we're going to use StatCrunch. Okay, which we can populate the data into StatCrunch and then, you know, click on a couple of places. I think use summary stats under summary stats. Okay, you're going to be able to get the quartiles. All right, and I'm going to do that in the homework demo. So if you want to see that in action, all right, be sure to check out the homework demo. Okay, but StatCrunch is pretty easy to use. So okay. Yes, so they showed a example using StatCrunch. All right. If you have TI-84 plus, okay, you can get that as well. Once again, I'm not sure if anyone uses Minitab. All right, so I'm not sure if Excel do quartiles. I have not looked at it recently, so I'm not sure about that. Okay, next. Interquartile range. Interquartile range is a simple calculation of the distance between the third quartile and the first quartile. All right. All right. So here, use interquartile range to identify outliers. Okay. So the idea of outlier is this. Okay. So let's say you have a bunch of data points. Whoops. Sorry about that. So if you have a bunch of data points, all right, um, let's say here's your distribution of data, okay, and let's say that you have a data point way out here, okay, way past everyone, okay, so this is what we're calling an outlier, okay, and could be problematic because it's going to throw off, as you well, as you can see, it does affect the mean at least, okay, and not to mention probably other calculations. So whenever we have an outlier, we need to really study it, okay, to make sure that one, it is a legitimate piece of data, okay, and two, well, a lot of times outliers are mistakes. So if someone put an extra zero, okay, or something like that, well, that will create an outlier. Um, Other times, it could be a data point that doesn't belong in the analysis. Okay, so you look at it and say, oh, that's a data from a demo or from something that is not part of the study. Okay, or something. Then maybe you want to exclude it. Okay, but you study it and then you determine whether it's justified to include it. Okay, and if it is not, okay, you take it out. It's what we call data cleaning. Okay, you hear about data cleaning, clean the data. Okay, which is what we do, when we take care of, things such as outliers. Now, but if, but how do we determine whether a data point is an outlier? All right, so here are the rules. All right, so first of all, we find the first quartile and the third quartile. Okay, so and then we find the interquartile range. All right, and then we're going to multiply that by 1.5. Okay, so 1.5, we subtract 1.5 from Q1. Okay, so let me draw a picture. Okay, so this is Q1, this is Q3. All right, so Q1 minus, let's say this is Q1 minus 1.5 times IQR. Think of it as a limit. Okay, this is like the limit, the outer limit, if you will, not the TV show. All right, and this would be Q3 plus 1.5 times IQR. Okay, so this is kind of like where we consider the normal range of the data. All right, And if you have data points beyond these two limits, okay, so this would be an outlier. Okay, that would be an outlier. Okay, so using IQR, we determine the extreme limits of where the data should be. And if you have anything beyond that, okay, it would be an outlier. All right. So so any data entry less than that or any data greater than that, okay, would be an outlier. All right. Okay, so here's an example. All right. So in a previous example, okay, from our data set, okay, we have Q1 equals 47, Q3 equals 58.5. All right. So the IQR is Q3 minus Q1, which is 11.5. All right. So um, where would it be the extreme, the outer limits? So outer limit here, outer limit there. All right. Um, so 1.5 times IQR is 17.25. So now I'm going to take 47, which is Q1, and 58.5, which is Q3. Okay, we're going to add 17.25 to get the outer limit here. Okay, and the lower outer limit would be 47 minus 17.25. All right. So let's see if they got the same thing. So, so their calculation, the outer limits are 29.75 to the left and 75.75 to the right. Okay, so a data entry less than 29.75 is an outlier. A data entry greater than 75.75 is an outlier. So 19, if that's a data point, 19 would be an outlier because it's less than 29.75. All right. Okay. Now, box and whisker plot is a chart of the data that shows you the the quartiles and the outer limits. All right. So the what it uses what we consider five important pieces of information from the data. We call it five number summary. Okay, so the five numbers that are kind of like the landmarks. Okay, the first one is the minimum data. Okay, the minimum number, and then the Q1 median is Q2, Q3, and then the maximum entry. All right, so those kind of form the box. Okay, and then we're going to do the whisker. I'm going to show you how to do that. Okay, so all right, so here's what it looks like. Okay, so the box is formed by Q1, Q2, and Q3. Okay, so Q1 and Q3 are the outer edges of the box. Q2 is the middle. All right. Now, the minimum X and maximum, those forms the whiskers. Okay, you can see the whiskers goes out and it draws out to the minimum. Okay, and on the other side, the whisker draws out to the maximum. All right. So in this example, so using the five number summary, okay, we can draw the box and whisker plot now. Um, so here are the five numbers, okay, that forms the plot, okay, and as you can see, the 19 is way out there. Okay, that's a long whisker on the left-hand side. Okay. Um, Now, the other interesting factoid about box and whisker plot is that the box represents about half of the data, okay, which would be between 47 and 58.5. And of course, it's half because, it's between Q1 and Q3, right? Okay, so Q1 and Q3 kind of box in, the middle half of the data, all right? And the left whisker represents about 1/4 of the data. Okay, so this is 1/4 here, this is 1/4 there, so the entire box is about 1/2. All right, and then the other quarter would be the right whisker, and then the last quarter would be the left whisker. Okay, the length of left whisker is much longer than the right one. Okay, so it's a possible outlier. All right. Any questions on that example? Okay. The the deciles, um, I don't really use that much, okay? But basically you're dividing your data into 10 portions, okay? Quartiles are used a lot. You divide the data into 4 portions. Percentiles also use a lot because we did divide the data into 100 portions, okay? So, but the deciles, not so much. All right. Okay, so let's take a look at the um, percentiles in action. Okay, remember the ogive? Yep, the ogive is a plot that uses the cumulative frequency. Okay, and one use of the ogive is that it's a good representation of the percentile. All right, so in this example, okay, we're looking at SAT scores. Okay. And if we make this plot, okay, and we can pick a score, okay, for example, well, actually, they want to look and see what score will put you at 90th percentile. So 90th percentile means that you're better than 90% of everybody. Okay, and if you drag that out over, okay, and you drop it down, and you're going to see that it's roughly maybe 1350. If you score 1350, you're better than 90% of the people who took the test. All right, so 1350, yep. So they got the same. Okay. It also means that 90% of the students got a scored, 13 score below 1350. Okay. Now, if you wonder the middle, what's the median? All right. So, what score means that you are like halfway. Okay. So if you look at 50 percentile, okay, and you drop it down, it's slightly over a thousand, so maybe like 1,050. Okay. That would be the 50th percentile. That means half of the people score above that and half of the people score below that. All right. Okay. So here is the next calculation, percentile of X. Okay. Is the number of data entries less than X divided by total number of data entries, which is reasonable, right? How many data points is less than that out of total data points? Okay, so let's see if we get an example. All right, here we go. So here is a data set, okay, and this is the tuition cost example. Okay, so we have a bunch of data. Okay, and we want to know, so what percentile corresponds to $57,000? So if I'm paying $57,000, what's my place in terms of percentile? All right, so let's see if we can figure that out. Basically, you're going to line up your data from, smallest to largest, and then see where 57,000 sits. All right, so if we put everything in order, okay, the number of data points less than 57 is 15. All right. Out of total number of data points, okay, there are 25 data points in that data, 25. So 15, you are at 15 out of a total of 25. So this would put you at 60th percentile. All right. So which means that you are you are paying more than 60% of the people, okay, but you're paying less than 40% of the people who are above you. All right. Okay. Any questions on percentile? Percentile basically it's what your position is, among the data points. All right. So the higher you are, okay, the higher the percentile. All right. Okay. Next. Okay, so now we're going to talk about the Z-score. All right. So, um, a few minutes ago, maybe a half hour ago, if you recall, when we were talking about the bell-shaped curve and the percentage of the chocolate cake, remember that? Okay. So, I would use the same example. We use as an example. Okay. The mean is 70 in a quiz. Okay. Standard deviation is 5 points. All right. So, if we look at a cake, chocolate cake, okay, 70 is in the middle of the cake. All right, if you score 75, okay, you're plus one standard deviation. If you score 80, you're plus two standard deviations, right? Okay, if you score 65, you're minus one standard deviation. If you score 60, you're minus two standard deviations, right? And if we look at the amount the amount of students score between plus and minus one standard deviation, for example. Okay, so proportion of students who scored between 65 and 75. Okay, this is roughly 68%, right? Plus or minus one standard deviation, this is 68%. So a quick recap of what we talked about 30 minutes ago. All right. And if we go two standard deviations, okay, from 60 to 80, okay, that's 95% of the data, right? So from 60 to 80, this is 95%, right? So guys, remember that, right? Okay. Yeah. Okay. So that's all good and stuff, okay, and cute, okay. But the math department comes along and say, okay, well, I don't care about 60 to 80, okay, but we have a cutoff at, for example, 72 for some reason. Okay, let's say, okay, we want to know what portion of your students score above a 72. Well, the rule, the empirical rule, the cake cutting that we were learning, okay, it has all different kinds of cuts, but it did not cut at 72. So how do we figure that out? Well, it turns out that there is a way to find out. Okay. Um, So we kind of what we need to do, okay, is we want to find out how many standard deviation is 72. Okay. And then once we figure out what standard deviation is 72, then we can find the amount of cake. All right. We can. Okay. As a matter of fact, I'm going to show you guys how to do that in a minute. Okay. Now, so how do I find the standard deviation for 72? Okay. We take 72 minus the mean. Okay. Mean is 70. Standard deviation is 5. Minus 70 divided by 5. Okay. Standard deviation is equal to this. Okay. Well, standard deviation is kind of a mouthful. Okay. And we hate to say that much just for a little calculation. So we give it a short name. We call it the z-score. Z-score is the number of standard deviations of the data point. So if we need to find a standard deviation of 72, we plug into the z-score formula and find the z-score. So the z-score formula is the data point, the point of interest, minus the mean divided by standard deviation. Okay, so 72 minus 70 divided by 5. So this is 2 over 5. This is going to be 0.4. So it turns out that standard deviation for 72 points is 0.4. All right. So now we need to find the amount of cake. Okay. Specifically, we want to find the amount of cake to the right. Okay, because we need to find what percentage of students score above a 72. Okay, so amount of cake to the right. Okay. And so how do we do that? With the 0.4. Okay. Well, I'm going to show you. Let's see here. All right, so let me bring out my next web tool. The next web tool you're going to learn. Okay, last time we used the standard deviation calculator. I don't know if any of you tried it, okay, but it's quite handy. And today I'm going to introduce to you guys the normal distribution calculator, or in other words, this is a z-score calculator. All right. I hope you guys can see it. It looks like you guys are looking at it. Whoops, nope. Let me see if we can bring that up.
Yeah, we can see it.
Can you see it?
Yeah.
Okay, I'm seeing. Okay, good. All right. Let me move this out of the way. All right. So this is a really, really handy thing. All right. Back in the day when I was learning statistics without personal computers, we had to use tables, which is a pain in the butt. All right. You guys don't have to use tables. All right. So I'm going to show you how to use the calculator. Okay. So the calculator, actually, the setup is quite simple. Okay. As you can see, let me wipe out some of the stuff. All right. All right. So there are just a few boxes here. Okay. So um, we have a z-score of 0.4, right? Okay. Z-score 0.4. So you put 0.4 where the z-score is, where it says z-score 0.4. All right. And I'm going to hit calculate. Ooh, look, what do we have? So what we have here, okay, it even show you a picture, okay? So you see the bell-shaped curve here, okay? This is z equals 0.4, or in our example, 72, okay? Now, it is shading the piece to the left. So I'm cutting the cake here, okay? And the portion to the left is the number that displays below the below zero point 0.4 that I entered. So this is 0.65542, okay? Which is about 65.5% to the left, okay? But we're not interested to the we're not interested in the left piece. We want to know the right piece. Okay, right piece is greater than 72. All right, so how do I get the right piece with the left piece? Okay, well, um, what we do is since the entire cake is 100%, right? So to get the piece to the right, I take 100% or 1 minus 0.65542, okay, which is 0.3446-ish, okay, or 34.46%. So that's the piece to the right. Okay, now the good thing about this calculator is that it actually have that calculated for you right here. Okay, so the piece to the left, they always show that to you first, and then it give you the piece to the right, 0.3446. All right, so that's your answer. The percentage, the proportion of students who score above a 72 on our quiz is 34.46%. All right. You have to say it's a pretty handy tool. Okay. I think, one of the best inventions in terms of math. So you have no idea how happy I see this. It's like, oh, I don't have to use that table anymore. So good. So easy. So quick. All right. Okay. So, any questions on how to use this thing? Now, in case you guys wonder, all right, um, if we are given the amount of kick, can we use it to find the z-score? The answer is yes. Okay. If we have the amount of kick to put in, then we would put into the bottom box, okay, and then hit calculates, and then we would get the number, the number for the z-score. Okay, so it works both ways. All right. And you're going to see plenty of this, in our demonstration for the next few classes, because we're going to be doing a lot of normal distribution and all that kind of stuff. All right. And I'm going to have the link of this web calculator posted in our classroom. So see, where is our lesson? Here we go. Okay. All right. Very exciting. The web calculator. Here we go. And in case you wonder, okay, of course, for the test, you can use the web calculator. You can use any web calculator that I presented in class, because, you know, um, since you're taking it on your own, so you should have access to it. All right. Okay, so let's go back to see. Okay, so here's an example of finding z-scores. So the mean speed of vehicles along a stretch of highway is 56 miles per hour. So 56, this is our mean, with standard deviation of 4 miles per hour. You measure speeds of 3 cars traveling along the stretch of highway. Okay, so car number 1 is 62, car number 2, 47, and car number 3 is 56 miles per hour. Find the z-score that corresponds to each speed. Assume the distribution is approximately bell-shaped. Okay, so once again, remember the formula to calculate the z-score. X, which is the data point of interest, minus the mean, divided by standard deviation. So for the first one, it's going to be 62 minus 56. 56 is the mean. All right, 4 is the standard deviation. So 62 minus 56 divided by 4. All right, so this would be 6 divided by 4, so it's going to be 1.5. Number 2 is going to be 47. 47 minus 56 divided by 4. So this would be 9 over minus 9 divide over 4. Okay, so it's going to be minus 2.25. And then the third one is 56. So 56 minus 56 divided by 4. So this would be 0 because it's going at the mean speed. Okay, so 0 over 4. So the z-score for the third one is 0. Let's see if they got the same thing. Okay, looks like they do. So first one is 1.5. Let me use a different color this time. So 1.5 and minus 2.25 for our second one. And the last one is 0. All right. Okay. All right. So now one thing that you can use for the z-score is to see how far you are from the data center. Okay, if you recall, okay, at the center of each data distribution, okay, the z is equal to 0. Okay, because you're in the center at the center. Okay, so if you have a data point, okay, um, let's say right here, let's say this is z equals to, I don't know, 2.2. Okay. And then you have another data distribution, and maybe this one has a larger spread. All right. And if so, the center would be 0 again. Okay. And then you have a data point out here, but maybe the z out here is only like 2.1. Okay. Why would this be? Well, that's because, if you have a larger spread, okay, then everything is more spread out, right? Okay, if a smaller spread, then everything is closer together. So if we have these two, if we're comparing these two data points in the two different distributions, okay, even though the first one is closer to the center, it looks close to the center, but it has a larger z-score. So this is considered, farther away from the center, even though the actual distance may be shorter. Okay. And this one with the bigger spread, okay, this is not as far away. Okay, so z-score tells you the relative distance of the data point away from the center. Okay, and we're going to see an example of that here. All right, so let's take a look. Okay, so for this example, we have men and women, the height, all right, and what we're looking at. Okay, so the height of men average 69.9 inches with a standard deviation at 3.0, and for women 64.3, and standard deviation is 2.6. All right, so men have larger range than women slightly. Okay. Okay, so let's compare, a 6 feet tall man and a 6 feet tall woman. Okay, and just to see, how they are in terms of distribution. So if we look at 6 foot tall man, all right, and we calculate the z-score, okay, so 72 inches, okay, minus the mean divided by standard deviation, we have a z-score, okay, z for man is 0.7, whereas for 6 foot tall woman, okay, we take the 72 inches minus the mean divided by standard deviation. This is roughly 3.0. So Z for women, okay, so even though, men and women are both 6 feet tall, okay, but for women, it is farther away from the average, okay, farther away, which means that you are less likely to see one. Okay, whereas for men, okay, it is not as far, so you're more likely to see 6 feet men than 6 foot women. All right, so that's the interpretation of the z-score. Okay, so this is farther away. Farther away from center. Okay, which means more rare. Okay, so this is closer to center, which means more common. All right. Okay, so um, here they're showing it, okay, using a picture. Now remember the cutoff that I mentioned a while back. Okay, the the cutoff is two standard deviations, or z equals to two. So z equals to 2 or minus 2, those are the cutoffs. All right. So if you have a z greater than 2, okay, which for the women it is, okay, because this is z equals to 3, okay, so this is unusual. All right. But for men, okay, at zero point 0.1, I mean 0.7, okay, this is what they call it typical. I would just say that it's not unusual. All right. Okay, any questions on that? Well, we have arrived at the end of our lesson tonight. No further questions from anyone? Okay, good. So what I'm going to do is I'm going to turn off the recording for about a couple minutes. I'm going to bring up the homework and I'm going to run through a few homework problems. You're more than welcome to stick around and join me. All right. If not, both recordings will be available for you to watch later on in case you encounter any problem with the homework and you want to see how I do it. Okay, so we'll get to do that. All right, so I'm going to take a break. I'll be right back.